Hello, I'm glad to see you again in another space-themed video. Do you know how scientists calculated the speed of light? Why are photons essentially the eternal doctors of the universe? Or why does the Earth rotate on its axis instead of standing still? Welcome to Mind-Blowing Facts About the Universe, Part 75. We know that if an alien race lived 65 to 66 million light-years away from us, and they pointed a powerful space telescope toward Earth to observe, they would see dinosaurs. This is simply because the light rays that departed Earth 65 million years ago would currently be exactly 65 million light-years away from us. Similarly, the image of the Sun you see every day is actually an image of it from the past, specifically 8 minutes and 20 seconds ago, which is the time light needs to travel from the Sun to the Earth. This implies that to travel vast distances in the universe, photons would need hundreds, millions, or even billions of years of wandering, right? If you've followed VFX for a long time, the answer is, yes, but also not exactly. It is true that from our perspective, photons emitted by the Sun take 8 minutes and 20 seconds to reach Earth. And photons emitted from Earth would take 65 million years, a span of time equivalent to millions of human lifetimes, to reach a distant alien civilization 65 million light-years away. However, for the photons themselves, it doesn't feel that long at all. In fact, they have no concept of time. Why is that? First of all, according to Wikipedia, a photon is an elementary particle. If you prefer something more advanced, they are quanta, essentially the smallest discrete unit of a physical entity, in this case, light. Photons are characterized by two properties: they have no mass, or an invariant mass of zero, and they always travel at the speed of light in a vacuum. I emphasize, they always travel at the speed of light in a vacuum. According to Albert Einstein's theory of special relativity, velocity-time dilation is the difference in the elapsed time measured by two observers, depending on the relative velocity between them. More specifically, Einstein argued that a clock moving through space will run slower than a clock that is stationary relative to an observer. Suppose we are on Earth, the faster a clock moves in space, meaning the greater its relative velocity compared to the observer, the slower it runs compared to the observer's clock. When it reaches the speed of light, time stops entirely on the moving clock, while, of course, it continues to run normally on the observer's clock. To put it simply, the faster you move through space, the slower you move through time. And when you move through space at the speed of light, you stand still in time. This means that an object moving at a speed extremely close to the speed of light could travel for billions of our years before a single second passes for the object itself. It also means that if photons wore watches, those watches would never tick, no matter how long they traveled. Furthermore, because they have no concept of time, photons don't have time to do anything, including wearing a watch, as I just mentioned. Along with that, they have no consciousness of their own existence, they have no past, present, or future. The entire process, whether it lasts 8 minutes and 20 seconds, 65 million years, or even billions of years, from the moment a photon is emitted and travels through space until it is absorbed by your eye, happens all at once from the photon's perspective. It takes no time at all. This inadvertently means that any distance in the universe, to a photon, is effectively zero. Everyone knows that the Earth rotates on its axis once a day, or more precisely, once every 23 hours, 56 minutes, and 4.09053 seconds. This is equivalent to a speed of about 465 meters per second or 1,673 kilometers per hour at the equator. However, not everyone knows why the Earth rotates. The answer is very simple: inertia. For those who don't know or have forgotten, inertia is the property of an object to resist changes to its state of motion. This means an object in motion tends to stay in motion unless acted upon by an external force. But why do we say the Earth rotates because of inertia? To answer this, let's step into the VFX time machine and go back 4.568 billion years to the time the solar system was formed. We know that the Sun and its surrounding planets were formed from the gravitational collapse of a giant cloud of dust and gas. Scientists believe this collapse was triggered by a supernova explosion of a nearby star. Notably, during the collapse, dust particles and gas molecules were pulled toward each other and began to spin around one another in a counterclockwise direction. It's not entirely clear why, but they spun counterclockwise, and because angular momentum is a conserved quantity, the Sun and the planets formed from that dust cloud had to keep spinning to conserve the angular momentum of the matter that formed them. Since the friction between the Earth and space is nearly zero, meaning there are almost no forces hindering the Earth's rotation, we say that inertia has caused the Earth to continue rotating on its axis to this day. I say, nearly zero, rather than absolutely zero, because the Earth is actually slowing down over time. Specifically, according to Wikipedia, a day in 2019 was 1.7 milliseconds longer than a day in 1919. That might seem trivial, but it means that over 4 billion years ago, a day on our planet lasted only a few hours. The culprit behind this time theft is none other than the Moon. To be more specific, you might remember the concept of tidal force that we presented in previous videos. Simply put, it is the difference in gravitational force on different parts of a celestial body caused by the gravity of another celestial body. The Moon's tidal force acting on the Earth does more than just pull the Earth's crust a few centimeters away from the center, raise sea levels by 0.6 to 16.3 meters, or stretch the atmosphere out by kilometers. It also slows down the Earth's rotation bit by bit over time. A computer simulation conducted by scientists Madia Cook from the SETI Institute and Sarah T. Stewart from Harvard University modeled the formation of the Moon using the giant impact hypothesis. It showed that when the Earth was newly formed, it likely spun nearly 10 times faster than it does now, with a day lasting only about 2.5 hours. A viewer named Dewey Holm wanted to know how people calculate the speed of light. Even if you aren't a physics expert, you likely know that velocity equals distance divided by time. If you apply this formula, you'll realize that the speed of light seems indeterminate at first. This is because, over short distances on Earth, light appears instantaneously. It seems to take 0 seconds to go from point A to point B. And try dividing any number by 0. That is why, before the 17th century, the scientific community believed that light traveled instantaneously. The great Italian physicist and astronomer of the 16th and 17th centuries, Galileo Galilei, the man dubbed the father of observational astronomy, modern physics, and the scientific method, once tried to measure the speed of light with the following experiment. He and his assistant each carried a covered lantern to the tops of 2 hills a few kilometers apart. Galileo would uncover his lantern, and the assistant would uncover theirs as soon as they saw the light from Galileo's. Galileo recorded the time from when he opened his lantern until he saw the light from his assistant's, hoping to calculate the travel time of light between the 2 hills. However, as mentioned, the speed of light is far too fast for such an experiment. The first person to actually measure the speed of light was the Danish astronomer Ole Romer. In 1676, Romer conducted observations of Jupiter's moon, Io, and noticed that depending on the positions of the Earth, the Sun, and Jupiter, there could be a discrepancy of up to 22 minutes between the predicted time of Io's eclipses and the actual time they occurred. He correctly hypothesized that this was because the time light takes to travel from Jupiter to Earth changes as the distance between the 2 planets changes. By doing the math, Romer came up with a figure of 214,000 kilometers per second for the speed of light. The error primarily came from the fact that planetary distances had not yet been accurately measured at that time. Since then, scientists have used many different methods with increasing complexity and accuracy to measure the speed of light. Ultimately, however, they all follow the principle of Galileo's lantern experiment: emit a light beam at one end, receive the reflected light at the other, record the time the light needs to travel that distance, and then calculate. One of the most accurate experiments was conducted in 1972. A group of scientists at the U.S. National Bureau of Standards used laser interferometry, a method of measuring the wavelength of electromagnetic radiation, to determine the speed of light in a vacuum as 299,792,456.2 meters per second, with an error margin of about 1 meter per second. By 1983, the 17th General Conference on Weights and Measures defined 1 meter as the distance light travels in a vacuum in 1/299,792 for 58 of a second. Therefore, the speed of light in a vacuum is now fixed and exactly 299,792,458 meters per second. In short, velocity equals distance divided by time.